Dear students, welcome to Statistical Physics 1. This is our course in fall 2020. This is my first lecture, and as we discussed during the daytime, we will start with the thermodynamics part of the course, and this will entail like 1/3 of the course, and later we will go on to proper statistical physics, which will include probabilities and ensemble theory. So let's begin. Starting with thermodynamics. So thermodynamic means anything related to heat, and dynamics means motion. So it is an old science. So it was formulated long ago, more than a century ago, and it was formulated to deal with practical aspects, and it involved energy, mechanics. Mechanics means work, potential energy, kinetic energy, so on and so forth. And it does not involve any rigorous physics like quantum mechanics or something like that. So it was merely based on some empirical laws, and to some extent to some laws of classical mechanics. But more emphasis was on practicality of this thermodynamics. So some thermodynamic quantities that you need to take into account while studying thermodynamics, these are internal energy, temperature, and heat. You might have studied these things in your previous courses. I would say internal energy is the total energy of atoms and molecules. So all type of energies that gas, for example, here we will discuss mostly gases. So for a gas, so internal energy will be is the energy of the system or energy of the atoms that does not give any macroscopic motion. So macroscopic means the gas does not move, or the body does not move due to this energy, but there is a potential kind of energy inside it. We don't call it potential energy, but we call it internal energy. Later, when we will do some examples, it will be clear what does it mean by internal energy. Second important terminology or concept is temperature, and that is the measure of our internal energy of the system that we defined earlier. Like, okay, so if internal energy is U, and if we can measure it somehow, we call this quantity as temperature. So you have known it beforehand that average kinetic energy of molecules of a gas is temperature. You know it beforehand. You have learned it during maybe your thermodynamics course, or also maybe in your FSC books. So temperature is the same thing, but here we give it a bit more sophisticated definition. So we say, okay, temperature is a measure of internal energy of a system. Third important quantity is heat. And heat, you know from day-to-day examples. Okay, so you go outside your room in the daytime, and there is a lot of heat coming from the sun. And there are several other examples of heat, like a burning stove, or a candle, or a light bulb. So you know what heat is. But in terms of thermodynamics, we say that heat is a way in which systems change energy in between them. It's a one way how they change energy in between them. So there can be another way in which energy can be exchanged, that is work, but heat is specifically the second way on top of work. So there can be two ways in which systems can change energy, internal energy, that is, one is heat, the other is work. Another important thermodynamic quantity is entropy. Entropy we will define here crudely, and later we will go on and explore what does it mean in more detail. For the time being, you can remember that entropy is a measure of disorder of the system. Later, when we will do physics, like statistical physics properly, you will get exactly the idea how does it mean by entropy. But for the time being, you say, okay, the measure of disorder of a system. So you arrange something in proper order, and then you destroy that order. That means the entropy of the system has increased. And in thermodynamics, one more thing to remember is that the change in entropy happens only, the change in entropy, it can be increased or it can be decreased when we add heat to the system or we remove heat from the system. So entropy can be understood in terms of heat in this way. I hope you get somehow a general idea of entropy. So it is related to the previous thermodynamic quantity, that is heat, and it is also related to the idea of temperature also, and we will discuss its mathematical form, but a bit later. So let's move on. I will briefly give you an idea of laws of thermodynamics. So the first law of thermodynamics is the law of conservation of energy. So it says that you can interchange energy between two systems with different methods, as I discussed before, but energy cannot be created or destroyed. So if you see now this equation, the equation of the first law, it is basically saying that your right hand side is du. This is the change in internal energy, and it is saying that it can be done in two ways. One way is that you provide heat or remove heat, and the other one is you do work, or the gas or the system itself does some work. And this sign can be positive or negative depending upon the situation. So it is not always negative, it is not always positive. So we define some conventions, we define some rules to define this sign. But normally you can say that, okay, you can interchange energy between two systems in two ways: by adding or removing heat, or by doing some work or getting some work out of that system. But overall total energy of the system is always conserved. At this first law of thermodynamics we will use more often than anything else. So you should be always aware of this law. You should learn by heart. You should cram this formula of the first law of thermodynamics, although you have already studied about it in detail in your previous courses. Okay, so first law is this, and then we have second law. So second law says that entropy of a system, entropy is a quantity. So for the time being you say that it's a quantity that measures the disorder of the system, and it says that entropy of a system always increases, isolated system increases in any irreversible process, and it remains unaltered in any reversible process. Now you have to open your eyes so that I can explain you what does it mean by the second law. So it says that there can be two types of processes. So one can be a irreversible process, this one, and it can be a reversible process. So irreversible process, you should consider it as a big process. For example, you have a glass of water and you spill it, and the water goes down on earth, and you cannot recover it in the same form. So this is a big process or a large process. So the reversibility is not so easy. You cannot bring the exactly same water back into your glass, or you can say that you have a cup of coffee, warm cup of coffee on your table, and you keep it there for some time, and after like 5 or 10 minutes it becomes cool, and then you cannot add that heat so easily to that cup. This exactly the same heat that has gone into the environment or into the air. So this kind of processes we call them irreversible processes. So it says, this law says that in these kinds of irreversible process, the process that cannot be reversed, that cannot be undone, for these processes, entropy always increases. So if you see now this inequality, so this greater than delta S, delta means change in entropy, greater than 0 means that this is the this greater sign is for this irreversible process. What is if the process is reversible? So if we do such a process that we can revert back easily, then entropy remains constant for a reversible process. But reversible process is not a practical process. It's a hypothetical, or what you call in a theoretical kind of concept. So there is in the real world there cannot be a reversible process. You will not see a reversible process so easily because it involves a really small amount of change. How small? The small that you can only imagine but you cannot perform. Maybe in this scientific world where we are living, so there are some irreversible process there are some reversible processes at quantum level, but they are not so easy. So, but because physics and thermodynamics are based on ideal conditions, so it says that for an ideal reversible process, the process that can be reverted back, the very small process, for that kind of process the entropy remains constant. So this equal sign delta S is equal to 0 stands for that kind of a thing. And in generality we say that this is the principle of increasing entropy. The second law is basically the principle of increasing entropy, because all real life processes are irreversible processes, and therefore this equal sign is seldom true. More often than not, this greater than sign is true. Okay, I hope you somehow get the idea of this concept. Okay, then we have third law. Third law is it's also related to entropy. So what does it say? It says that entropy of a system at absolute zero is minus 273.15 kelvins. You know this temperature scale, no? These are 3 temperature scales. So we say that there is a Celsius scale that runs from 0 to 100. 0 is the freezing point of water and 100 is the boiling point of water. And we have then Kelvin scale. So Kelvin scale is from 0 to up to any temperature. So on Kelvin scale we have 273 degrees, 273.15 as the freezing point of water, and 373.15 is the boiling point of water. And we have another Fahrenheit scale in which we measure the fever, and we say that okay, one has a fever when his or her temperature is greater than 100 degree Fahrenheit. So these are 3 scales, but in physics and thermodynamics we will use Kelvin scale. You should always remember that Kelvin scale is used in all thermodynamics and statistical physics and any other branch of physics that we use to measure certain physical properties. So third law says that at absolute zero, meaning at minus 273.15 Kelvin, how much? I must write it here somewhere. That is minus 273.15 Kelvin. The entropy of a true equilibrium state. Equilibrium state, I will show you what is that, but okay, for the time being, you just assume that it is a system that is at minus 273.15, and the third law says that entropy of a system is 0 at that temperature. At absolute 0, it is 0. Okay, this is not minus 273 degree Celsius, and it is equal to actually 0 Kelvin. I was that's my mistake. So this is the temperature. Okay. So at minus 273.15 degrees Celsius, which is equal to 0 Kelvin, we call it absolute zero. We call it absolute zero. The entropy of a system is 0. And this is interesting. Okay, we have said that this is a law, and entropy becomes 0, but entropy of a system cannot be 0 because you read the second statement. It says that it is impossible to reduce the temperature of a system to absolute 0. So we cannot reduce the temperature of a body to minus 273.15 Celsius. So entropy is never 0. Although theoretically we say that okay, this can be 0, and at minus 273.15 degrees C, the entropy will go to 0. But in practical applications, it is impossible. We cannot attain that much temperature, that kind of low temperature, that minus 273.15 degree C. So this law is really interesting, and it is a basis of very, very interesting phenomena that if you will study physics, you will get the idea what that law means. Okay. Next, I will discuss a bit about the history, why thermodynamics was invented or developed. So the development was related to practical aspects, because at that time there were heat engines like steam engines and coal engines, which used to run factories, and used to run trains, and they the problem of these engines was that they were not efficient. So they took a lot of input, like a lot of coal or a lot of oil or a lot of any fuel, but they produced really small amount of work. The efficiency was okay, 10 to 20% maximum, 40% or something like that. So people at that time were keen to develop efficient engines, and for this kind of purpose, they used to study the efficiencies, and they used to say, okay, if we have some kind of ideal engine, then it will take some amount of fuel, like for example 1 liter of oil or 1 liter of petrol, and it will convert completely this amount of oil to energy, and it can have 100% efficiency. Although they never achieved this kind of efficiency, but they theoretically developed models. So you might have heard about Carnot engines and blah blah blah, and those Carnot engines were ideal engines. They used to fancy those kinds of engines. They used to think that okay, if we had this kind of engine, okay, we will be really lucky, and we would convert every drop of our fuel into energy, and we will be really prosperous and happy. Although they were not successful in that, but they developed really strong theory about that, and that theory is thermodynamics. Okay, and because they were developing these kinds of engines at that time, so the second law that we said, okay, the entropy always increases for an irreversible process, and it remains constant for a reversible process. This law was not exactly in this shape. So there were other statements of this law used by those people, those early people. So there was another statement that is written on your screen here. So that it says that no series of processes is possible whose sole result is the absorption of heat from a thermal reservoir and complete conversion of this energy to work. So second law, when they were imagining those ideal engines, so they thought, okay, this is not possible to create an ideal engine. And this feeling and this thought that they cannot create an ideal engine was the statement of second law. You see, it's written. So they said though no series of processes mean no such engines is possible whose sole means complete or overall process result is the absorption of heat from a thermal reservoir and complete conversion of this energy into work. So they said, okay, they admitted at that time that no such process can be obtained, or no such engine can be made which can convert every bit of energy to work. And this is written in somehow condensed form, like there are no perfect engines. This is also statement of the second law of thermodynamics. So there is another definition that does not involve any entropy. So that is what. So it says that no series of processes is possible in which the sole result of the is the transfer of heat from a reservoir at given temperature to a given low temperature to a given higher temperature. Given, you can write low also here so that you can understand it better. So it says that you cannot transfer heat from a colder body to a hotter body as such. I mean, heat cannot flow like that. Heat flows from it can flow easily from a hot body to a cold body, but if you want to transfer in a reverse process like refrigerators do, you cannot create an engine that takes heat from a cold reservoir and that directly puts into a warm reservoir. So I mean, you have to do substantial amount of work from outside to do that process. So that kind of substantial work is done in our household refrigerators and freezers and these kinds of ACs, for example, air conditioners. So we supply a lot of electricity to them. So there is a complex process of gases and condensation and sublimation and so on and so forth. And then you get as an end result that you have a small compartment we call freezer and a little bit bigger compartment known as the fridge compartment, from where it takes heat which is already cold, and the system takes heat from the colder portion and throws it outside. I mean, throws it into the room which is already at higher temperature. So the temperature inside refrigerator is, for example, at 5 degrees or 4 degrees, and in the freezer compartment it is 1 degree or 0 degrees Celsius, but outside it is already 40 degrees or 45 degrees. So this is doing this kind of process, but it is taking a lot of energy and it is wasting also a lot of energy to do that process. But there is no perfect engine that can do efficiently this kind of stuff and without dissipating energy. And this is also variation of second law of thermodynamics. You should give some attention to this law. These things are really interesting if you pay some attention. And third law, as we already spoken. Okay, so this is okay. One more time, it is here. So popular variance. I will leave these statements to yourselves. You should read them and try to understand what that means. So we can somehow condense these thermodynamics laws into smaller statements. So first law is you cannot win. Second law is you cannot break even, and the third law is there is no point in trying. So you can. We will discuss this in the class what these statements mean, and I will ask you, each one of you, what do you understand by this? I will not explain these statements here. So I will get to know your opinion on these three statements on slide 12. We have another law, but okay, so we know call it Zeroth law. So I will not go to statistical mechanics of the timing, so I will discuss Zeroth law. So Zeroth law was actually discovered after the third law, but it was so basic that they could not put it, I would say, before first law. They wanted to put it before first law, but they could not replace first law with this law. So they say, okay, we put it one somehow one standard behind that, so we call it zeroth law. So it was a basic law, but it was somehow discovered later, or they thought about it on later stages. So they call it zeroth law. So normally we should have started with zeroth law, and then we have studied first, second, and third law. But due to this historical perspective, we are doing in the same manner as the people who discovered this law used to do. So okay, so zeroth law says that if two systems are separately in thermal equilibrium with a third system, so this is very easy to understand. So it says, okay, we have two systems that are in thermal equilibrium. Thermal equilibrium means they have same temperatures with a third system. Then they are equilibrium with each other. Then their equilibrium means their temperature. Thermal equilibrium means their temperature is the same. How we signify that? Okay, so how should I explain it? So for example, you people are in Lahore, so one person is at N block outside in the sunshine. So that person is in thermal equilibrium with the temperature of COMSATs. Okay, that is, for example, 40 degrees Celsius or 42 degrees Celsius. There is another person that is in A block, or in inside physics department, but still he is inside outside in the sunshine. So that person is also in equilibrium with the temperature of COMSATs, although they are far away from one another, but they are in thermal equilibrium with the same bigger third system, and the third system is COMSATs. And this zeroth law says that if two separate bodies are in thermal equilibrium with a bigger third body, they are also thermal equilibrium with each other, which means that the person in N block and the person in A block both have same temperature, because they are in thermal equilibrium with the outside temperature of COMSATs. However, the condition can change. For example, if the person goes inside into air conditioned room, then the situation will definitely change, and then he has moved out of the thermal equilibrium of the sunshine, and then their temperature will not be the same, and then zeroth law will not apply. And diagrammatically, this situation is illustrated here. So we have two separate compartments. They are thermally insulated from one another. So here we have a body A that is connected to a thermal reservoir, and it has some temperature. And in this second compartment, we have now a body B which is connected with the same reservoir, thermal reservoir. So if this is the situation, that this thermal reservoir and this thermal reservoir has same temperature, this also means that A and B now have the same temperature, or we can connect them, and it is the same situation like this. Okay, so this is intuitive. I hope you have understood these concepts somehow. And this is the end of our first lecture. Next time we will do some more stuff in thermodynamics, and things will start to become a bit complicated. Thank you for your attention, and bye bye.